necessary. The most efficient way to send a spacecraft to the moon is to boost its speed while it is in a circular orbit about the Earth, such that the new orbit is an ellipse. The boost point is the perigee of the ellipse, so that's right here, right? That's the perigee. This would be the complete ellipse, right? And if I drew it well, it would look better than that. And the point of arrival of the moon is apogee, and so this point here is what we call R1, and this point here is what we call R0. And we're assuming that the height above the surface of the Earth is negligibly small, so it's 100 miles up or something, and the Earth's radius is 4,000 miles. We just neglect that. And so we're saying R1, which is the apogee, is 60 Earth radii, and R0 is 1 Earth radius. And they want to know, calculate the percentage increase in speed. So after you give the boost, we call that like V1. I think it calls it in the example, I think it calls it V0 is after boost, after you fired your rockets, and V circular is before. And of course, it's sort of instantaneous, right? It all happens at the same point. And so if you look at before, you can say, well, if you remember the lattice rectum, alpha is 1 minus epsilon squared times the radius of the orbit times the semi-major axis of the orbit, but that's just 1 minus epsilon squared times R0 because the orbit's circular, and so that's what that is. And since the orbit's circular, it's just R0 is equal to alpha, and that's just ml squared over k. If you remember that when we set up that differential equation, this is what we had. This is what alpha came out to be equal to. And so this gives us a relationship between the angular momentum and R0. So R0 is m times the L is the angular momentum per unit mass, and that's just R0 V circle squared. Those are both squared over K, right? The angular momentum is R cross P, or RP sine theta, which is MVR sine theta. But little l is the angular momentum per unit mass, and so it's just RV sine theta. But at perigee and apogee, theta is 90 degrees. That is to say, the R is this way, and the V is that way. And so you just get R0 times the circular orbit speed. And so if you notice, one of those R's cancels, and that makes that a 1. And when you get it here as a relationship, gives you R0 is equal to, you have to divide everything out, K over M V circle squared, or the way we're going to substitute it is, a little later, is K is equal to M R0 VC squared. Remember, K is just G M M. So what we have...
You're off the screen.
I'm off the screen? Thank you. What we have is, so that's the expression for K. What we have is the, now is a relationship between K and R0 in the circular orbit. And now we're going to try to kind of do the same thing for the elliptical orbit. So if I say after, now I have this sort of the same thing I had before. I have R0 is equal to 1 minus epsilon squared I've lost it. Stop for just a second. Alpha is equal to... Pull notes. Sorry, I was trying to do that off the top of my head. Let me just pull my notes up here. So alpha is equal to 1 minus epsilon squared times A, where A is the semi-major axis. And so that's equal to 1 plus epsilon times 1 minus epsilon times A. But 1 minus epsilon times A is just R0 because in an ellipse, let me just draw it over here. Here's the center of the ellipse. This little piece between the center and the focus is epsilon A, and the whole length is A, and this piece is R0. I don't know if you can see that, but so you'll just have to check your geometry. So this is alpha is equal to 1 plus epsilon times R0, or 1 plus epsilon. You can write it either way. All right, I'm going to have to erase. And so I'm going to kind of start with this equation and just mess with it a little bit. If I solve that for epsilon, I get epsilon is equal to alpha over R0 minus 1. And so that's equal to ml squared over k divided by R0 minus 1. And that's equal to that guy cancels with that guy, and I get the eccentricity plus 1 is equal to m v0 squared R0 over k. And so this v is the velocity after it's been boosted. And if you remember just a minute ago, I said k was equal to mvc squared R0. When we did the same little procedure for before it had been boosted, we got k was equal to this. And so the m's go away and these guys go away. And you get the ratio. This is the thing you're after, what the fractional increase in speed is. It's equal to epsilon plus 1. And so if you have to figure out how to calculate this from what you know about the ellipse, right? And so it turns out that R1, we just said earlier, we said R0 is equal to A minus epsilon A. And then R1 is equal to A plus epsilon A. So once again, here's my ellipse. I may be off screen. I'm off screen a little bit. Here's my ellipse, right? This piece is R1, and this piece is R0, right? And this piece is A, and you know these two pieces are epsilon A. And so A minus epsilon A gives you R0, A plus epsilon A gives you R1. And so you can figure out how to solve for epsilon if you do this guy minus that guy. So R1 minus R0 is 2 epsilon A. And then R1 plus R0 is 2A. And so epsilon is equal to, see if I can get this right, R1 minus R0 over R1 plus R0. Again, R1 and R0 are the things you have. This is 60 Earth radii, and that's 1 Earth radius. So you get V0 over VC squared is equal to, I'll erase that, this quantity plus 1, R1 minus R0 over R1 plus R0 plus 1. If I cross multiply, I get 2R1 over R1 plus R0. And so V0 over C is equal to the square root of that, 2R1 over R1 plus R0. And so R1 is 60 Earth radii, and R0 is 1 Earth radius. And so this is, 120 radiuses of the Earth over 61, which is about 2. And so the square root is about 1.4. Sorry, that's BC. So, these problems are using a little bit of the physics and a little bit of the geometry of the ellipse. And so you just have to wrestle with those two a little bit to work them out. The next thing I was going to do, let me just pull up the notes here.
So is 1.4 just like a special number or something?
I'm not sure what you mean by that. So this number came from the fact that this ratio is 60. I don't think we made any assumptions beyond that. So if I wanted to put the satellite in an elliptical orbit that was 80 Earth radii away, yeah, it would come out to pretty close to a factor of 2, wouldn't it? Is that what you're saying?
Like the homework problems, there's 2 answers that are 1.4.
Well, let me go the other way. Let's say we just wanted an elliptical orbit that was twice the radius of the Earth, right? Then that would be a little different, right? Because that would be 4 over 3, the square root of. And so, yeah, I guess in the limit that it gets really far away, the ratio is the square root of 2, which says that's pretty close, I guess, to the. I think what it's saying is that you're getting pretty close to the escape speed. By the time you've gotten to the moon, any further distance than that doesn't take a whole lot more energy. I think so. You're pretty close to having. If you've gotten to the moon, you've pretty well escaped the Earth's gravity, and so getting from there to infinity is going to take you a much bigger boost. I guess that's what it's saying. And so, yeah, that's a really good question. I'd have to think about it past that. It has to do with the fact that where the surface of the Earth is, because that's the ratio that kind of matters. But basically, if you're starting in really close, by the time you've gotten 60 times farther away, the gravitational force is diminished significantly, I guess. That's all I got.
Yeah, I mean, it's just weird to get, like, I don't know. I feel like whenever you get the same number over and over again,
Yep.
Maybe something to it.
Yeah, I get it. Yeah, I agree with you. All right, hang on a second. That's the ellipse. All right, I'm going to do the third law here real quick. This is just a short section out of your book, and I don't really have much to add to what they say there, really, but let's just talk about it just so that we've all said it. So Kepler's third law, we've derived the first two. I've got videos for all of these if you want to just look at them online. So basically, the third law says the square of the period, they use a tau, is proportional to the cube of the semi-major axis. And there are lots of ways to show it. When we do in GP1, I just do mv squared over r is equal to gmm over r squared. And when you do that, where v is 2 pi r over the period, you get the relationship right out. The catch is, of course, this is assuming a circular orbit, not an elliptical orbit. And so the proof they do in the book uses the stuff we did in for the second law, where we said the area, dA dt, this is what we derived right at the very beginning of the chapter, which is A dot is the angular momentum over 2m, the magnitude of the angular momentum over 2m, which is constant. We sort of proved this. And so then what you can do is you can say, well, let's integrate dA dt over one period, right? And that just gives you the area, right? And so the area, and it's equal to 2L over M times the period, right? Because dA dt is just 2L over M. And so this is a constant. If I integrate this over the time, I just get 2L times the period. And so this is equal to 2 little l times the period. And so what we get is the area of the ellipse is equal to 2L times the period. And then we're just going to mess with this thing a little bit. And so we're going to say, look, the period is equal to the area of the ellipse over 2L. And here you have to grab a little geometry. That's pi AB, where A is the semi-major axis and B is the semi-minor axis. It's the area of an ellipse. And that's over 2L. And in your book, I go into this, but the semi-minor axis of an ellipse is the square root of 1 minus the eccentricity squared times the semi-major axis. That's the relationship between those two. And so that means that tau is equal to pi a squared times the square root of 1 minus epsilon squared over 2L. Over, I've lost something there. Oh, I got it backwards. The 2 is up here, right? 2L times the period. The area is 2L times the period. Oh boy, I messed it up all the way back at the beginning. It's L over 2M. It's L over 2M. There's Sandra when I need her, right? This is L over 2M. This is L over 2M. So I got all my 2's in the wrong place. That's what I get for not looking at my notes. And so the 2 goes up here because the 2 is, I have to multiply by 2 and divide by L. And so that's why I get a 2 here, and not a 2 here, but a 2 here. Ugh. Sorry, guys. And so now we want the period squared. And so we're going to square both sides of that. And we're going to get the period squared is equal to 4 pi squared a to the 4th, 1 minus epsilon squared over L squared. And now you just have to do a little fancy geometry with this and say, well, if you remember the lattice rectum alpha is equal to 1 minus epsilon squared times A. And so 1 minus epsilon squared is equal to the lattice rectum over A. I don't know if you remember, but the lattice rectum was, if you started a focus and go perpendicular to the long axis, that distance is alpha, the lattice rectum. So you started a focus and go straight up, and that's 1 minus epsilon squared times A. Whereas if you go at the center, it's the square root of 1 minus epsilon squared times A, and that's B. Those are all in my videos. So, and you can just get to it by looking at the, I think you can just do a little geometry on that ellipse that's in the textbook. And so what we're going to do is we're going to take this guy and stick him in for that. And we're going to get the period squared is equal to 4 pi squared a to the 4th times, and so that's alpha over A divided by L squared. And if you remember, the lattice rectum is equal to m L squared over K. That's what we did at the very beginning. We're looking at the first law. And so I'm going to substitute that in here as well. And I guess I'll just erase the top. And so I'm going to write the period squared is equal to 4 pi squared A to the 4th times over L squared. So that takes care of this piece of it. And then I'm going to write m L squared over K A, right? This alpha here is ml squared over K, and this A is an A there. And so this A cancels that A, and that leaves me a 3 there. The L squareds cancel, bam, and bam. And K is equal to G MM. And so this gives me 4 pi squared A cubed M over G MM. This M cancels that M, and we get 4 pi squared A cubed over G times the mass of the Earth or the Sun or whatever it is you're orbiting. That's the period squared. Of course, Kepler didn't know this. Kepler just knew that if you took things that were orbiting the Sun, the period squared over the semi-major axis cubed is equal to a constant. Newton showed that that was 4 pi squared over G times the mass of the Sun. And so, you know, if you evaluate, so I think they have an example in here. Let me just see if I can do an example. So one of the examples says, what's the period of a comet with a semi-major axis of 4 astronomical units? And so this is a pretty easy calculation because it's orbiting the Sun just like the Earth is. And so I can say, look, the period of the comet squared over the semi-major axis of the comet cubed is equal to the period of the Earth squared over the semi-major axis of the Earth cubed. Right, and that means the period of the comet squared is equal to, I should put an E there, it's equal to the area of the comet, sorry, the semi-major axis of the comet over the semi-major axis of the Earth cubed times the period of the Earth squared. Right. And so So the ratio of the semi-major axis of the comet to the Earth is just 4-to-1. Uh, um, the semi-major axis is 4 astronomical units. You may not know, but an astronomical unit is defined as the radius of the Earth's orbit. And so AC over AE is just 4-to-1 by the definition of the astronomical unit. And so 4 cubed is 64. The period of the Earth is 1 year. We can leave that unit if we want, and this will come out in Earth years. So it's 64 Earth years is t squared. And so the period of the comet is the square root of 64, or 8 years. Of course, you could do anything that way. You could figure out, and by the way, it's pretty consistent. The orbit of Jupiter is about 12 years. And so this would be 5. Um, uh, Jupiter is about 5 astronomical units, and so 5 cubed is 125. Square root of that is a little more than 11. So it's not exactly 5, but all of those work. The book has a nice table of them. By the way, this comes, I'll just, in like 3 lines, I'll do it the way I did it in GP1. We just said mv squared over r is equal to gmm over r squared, and then v is 2 pi r divided by the period. I should use the same r's for these guys. And so this gave us the mass times 4 pi squared r squared over the period squared times r, right, is equal to g m over r squared. And so the m's cancel, right? And this r cancels with one of those r's. And then if I want the period squared, to solve for the period squared, I get the period squared is equal to, so I multiply it over here and divide those guys to get 4 pi squared r cubed over gm, which is just what we calculated, except a little more generally because we allowed it to be an ellipse.
So if we put that on the test, is that correct, or?
Well, it's not correct. It's not a correct proof of Kepler's law because this assumes that the orbit is circular. And so if I asked you to prove Kepler's law, which I probably wouldn't, but I don't suppose I could rule it out, you'd have to do that for an ellipse.
Fair.
I think the real question here is, would you ask us to prove Kepler's law on an exam?
Would you have a hard time with that? Like, do I just throw that back at you? What was hard about, I guess what was hard about that, really, to me, and by the way, I was doing this when I was doing the proofs. I kept having to go back and look at that ellipse picture, right? So you might want to, just a tip from me, I'll tell you what, if you want, you can copy the ellipse picture and use it on the test. So the ellipse picture and all the definitions below it, down to R0 and R1. Are you with me? So look at page 233. Up to equation 6.5.15. So just the picture, just the figure and all the definitions underneath it, not the equations. You should have enough information there to solve all the things you need. I think that's what I keep going back to. I keep forgetting which thing is which. Pretty well, every time I teach, I have to relearn that stuff. So, Where are we at? All right. I did some videos on a few of these things, and so I'm going to skip ahead a little bit, and you're just going to have to be responsible for those. So 6.8 just talks about, 6.7 and 6.8 just talks about um, potential energy in a gravitational field. And so I'll just give you a short sort of summary. You know, the potential energy is equal to it's basically equal to the negative of the work done. You end up with, for a central field, you end up with negative G mm over R is potential energy. And then they talk a little bit about, do you remember electric potential? What is electric potential? Somebody tell me.
Dr. Trell, you're off screen just a bit.
How's that? So this
Much
is
better.
potential energy in a gravitational field. Do you guys remember from E&M? What is another name for electric potential?
Voltage.
Voltage, right? And voltage is what? What are the units?
Potential energy in an electric field.
Say again?
Potential energy in an electric field.
Sort of. It's the potential energy per charge, right? The units is volts. Volts is joules per coulomb. And so it's potential energy per charge. And so a lot of people like to use that in so we call that electric potential. And so in this section, they define the gravitational potential, which is the potential energy. So this is the thing they call V of R, right? It's the potential energy per mass. So instead of electrical potential energy per charge, gravitational potential is gravitational potential energy per mass. And so this is like a generalized little g kind of thing. Or I should say, what do I want to say? It's not, how about this? Generalized gravitational potential. So the force is equal to minus del on V, right? If you know the potential energy, that's how you get the force, right? Little g is minus del on phi. And so if you multiply this guy by the mass, you get the force. And so this is kind of like your localized acceleration. The gradient of this thing is like your localized acceleration. In the same way that the gradient of the electric potential is the electric field, right? E equals minus del on V, where that's your electric potential, not your potential energy. All right, that's a zip through that one. 6.8 basically says, so any central force is conservative. Remember, del cross F equals 0 shows that we did this back in, I can't remember which chapter it is. Is it 2? Can't remember. I think maybe it's 4. I know 3 was a similar rock house, so there's probably 4. Anyway, del cross the force equals 0 means it's conservative, right? And it turns out that any central force, that is any force where the magnitude of force only depends on the distance from the center and not on any direction, not on theta or phi. Has to be conservative, and they just show it in there by doing del cross F in spherical coordinates and showing that the result of that is 0, and it's not too hard. So I'll leave that to you guys. And I'll talk a little bit about energy. So we've got a little time. So if I want to do an energy equation for orbiting bodies, it's it just says, look, if I have the Earth orbiting the sun or the space station orbiting the Earth, its kinetic energy plus its potential energy is a constant. And this gives us an energy equation for the object. And so this is just 1/2 mv squared plus, in this case, the potential energy, which is minus gmm over r is equal to E. And so we're going to use polar coordinates. And we're going to write down an equation for this. And it's a little ugly, right? Because it goes all the way back to when we were calculating the first law. You know, V, if I look at, so V squared is V dot V, right? And V is equal to R dot, which is dr dt, which is equal to d by dt on r e hat r. And this takes us back even to chapter 1, right? And so the velocity is equal to r dot e hat r plus r theta dot e hat theta. Am I still on board? Running out of room. And since E hat R and E hat theta are perpendicular, that is, E hat R points in the direction of the particle and E hat theta points, you know, along the theta direction. So it's always perpendicular to E hat R. Then V squared, which is V dot V, sorry, which is that kind of dot, which is V dot V, is just equal to R dot squared plus R squared theta dot squared. And so now I have a fairly complicated equation because I have, if I go all the way, so if I want to take this thing, right, and stick it in there, right, so that gives me a 1/2 m times R dot squared plus R squared theta dot squared minus G mm over R equals a constant. And so just like we did for chapter 1, or I mean for the first law, for Kepler's first law, we want to break this down into a time independent equation. And so I'm just going to leave that there for a second. We use R, just like before. This will look really familiar. R equals 1 over U. And so that means R dot is equal to minus 1 over U squared du dt. And that means, and that's equal to minus 1 over U squared. We use the chain rule, du d theta dt, and that's minus 1 over U squared theta dot du d theta. And so that kind of tells us something about the R dot squared. And then if you remember back to how we dealt with theta dot, we said R squared theta dot is the angular momentum per unit mass. We did that when we were calculating Kepler's second law, probably in the first section of the chapter, right? And so that means theta dot is equal to u squared times L, because I would divide out the r squared, and since u squared is 1 over r squared, that would give us that. And so if I wanted to write all this out again, right, I would say I would stick this guy in here, right, and in here, and I would get for this equation at the bottom, I would get a 1/2 m times, so r dot squared is going to be, I'm just going to write it out first loosely, minus 1 over u squared theta dot du d theta plus r squared. This is going to be a hybrid form because it's going to have some r's and some u's. I'm going to erase this line now, and I'm going to put a theta dot squared in here, but that's this squared, so that would be u to the 4th L squared minus g m m over r. I'm going to just write that as k, because it could be any 1 over r squared, right? Equals e. And so now I have some work to do. First of all, this is just a u squared. Sorry, 1 over u squared, and so I can make that a 2. And then I want to stick this guy in here, and so I get a 1 over 2m minus 1 over u squared, and I'm going to put in, for theta dot, u squared L du d theta plus u squared L squared minus ku equals e. So those guys cancel. Feel like I've lost an L somewhere. All right, let me check my notes real quick. Oh, sorry. This whole thing, now I'm on it. This whole thing is squared. This was r dot, and this whole thing is squared. That's what I lost. Right, the thing in the square brackets is r dot, right? That's what this is, and it's r dot squared, and so I lost a squared there. I think I'm okay. And so if I can factor out an L squared, and I can say 1/2 m L squared d squared u, no, not d squared u, du d theta squared plus u squared minus ku equals e. And so this really is the energy equation for the orbit. And it turns out you can solve this. This is instead of, when we solve the equations of motion, the force equations, we got a second derivative. Here we don't get a second derivative, we just get a first derivative squared, which is kind of what you expect because it's a velocity squared term, which is a first derivative. And so, but you can rearrange this a little bit, and I guess I will. Oh, I'm out of time. Well, all right. Let me just do this just for a minute. You guys can chime out if you've got someplace else to go. But I can move the KU over the other side and the ML squared over 2, right? And I get d squared, sorry, man, I keep wanting to make that a second derivative. du d theta squared plus u squared is equal to, and so it's 2 over ml squared times e plus ku du d theta is equal to, I don't know what best way to write this. I'll just leave it like this. Well, let me just write this way. 2e over ml squared plus 2k over ml squared u minus u squared. This is a constant. This is a constant times u. This is a constant. This is just a constant times u squared. And so I can separate variables. I can write d theta equals du over this mess. And it turns out when you integrate this thing, you get the exact same equation for u in terms of theta. It gives you r is equal to alpha over 1 plus epsilon cosine theta, just like the orbital equations expected showed it would. Except it gives these, it embeds the energy into this. And so just look at I'll have the notes posted here in a little bit, and you'll see how the energy plays into this. If the energy is negative, you get a closed orbit, like an ellipse or a circle. If the energy is 0, that is to say the total energy. If the total energy is negative, the particle is trapped. If the total energy is 0, it's a parabolic, and the particle just has enough energy to escape. And if the energy is positive, you get a hyperbolic orbit. That is to say, when the particle is at infinity, it still has kinetic energy left. All right, I'll stop there. I'll have some videos up in an hour or so, something like that, and I'll try to give you some ideas for problems. And if you want to send me a homework over the weekend, I'll send you solutions.
So is there any like I hate to say a test bank, but like what are possible like problems you're gonna ask? Are they gonna be like the homeworks we've done?
I'll try to give you an idea about that. Maybe I'll put some notes up online. I haven't written a test, and so, but was the last one shocking?
The number 9?
No, the last test.
I mean, I prepared for it like I would any other test, and I felt like when I got the test, I felt like it was way harder. Just because we hadn't been in class talking about what we're about to have the tests over.
Well, I guess I don't want to give you super long problems, but certainly some of the homework. I'll try to point to some of the homework problems that you can look at.
Yeah, I just generally have it narrowed down between like 10 problems, and like for the last test, I didn't have it narrowed down at all, and like my note card was almost rendered useless.
Okay. All right. Anything else? All right, you guys. Thanks for coming.
Any notes that you post, I would like those too.
Okay.
So, are these videos going to end up on YouTube? Are they going to be posted somewhere?
Like the note for this class right now.
Yeah.
You know, this is the first time I've actually recorded one of the lectures. I don't know how to get it up there, but I'll try to put it up.
All right, thanks.
Yeah.